Hi there, folks. Today we're looking at perpendicular and angle bisectors. And one of the things we're going to investigate as we look at perpendicular and angle bisectors is we're going to compare the distances here between different things, all right? And so this idea of things being equidistant, all right, just means that they're the same distance away from some other thing, all right? So if I say 2 points are equidistant from another point, it means that those 2 points are the same distance away from that third point. All right. So when two objects are the same distance away from a third object. All right. And we'll compare different types of things here. We might be comparing points that are the same distance away from other points. We might be comparing points that are a point that's the same distance away from two segments, something like that. And one of the important things here when we talk about distance is making sure we always measure the distance as the shortest distance between two things. So like when we're measuring from a point to a line, all right, we have to measure perpendicular to that line. We have to measure the shortest distance between the point and the line. We can't kind of measure on a diagonal because that would give us a false distance. That would give us a distance that's longer than the shortest path. Okay, so whenever we measure things, we measure the shortest path. Just like if you measure your height, you start at the ground and you measure straight up to the top of your head. You don't measure from the corner of the room to the top of your head on an angle, because then everybody would be able to claim that they're 12 feet tall. All right, so you have to measure the closest distance possible. And so keep that in mind as we start to measure distances. You're going to see right angles pop up a lot here, because when we measure a distance, we have to measure at a right angle. That's the shortest path from one thing to the next. Okay, so equidistant is when two objects are the same distance away from some other object, some third object. Okay, so let's talk about the perpendicular bisector theorem. Okay, so if I have a perpendicular bisector, so in this scenario, M is a perpendicular bisector to AB, and I basically want to prove that if some point C is on this perpendicular bisector, so notice there's some random point C there, I just want to prove that C is the same distance from A as it is to B. Okay, and so the idea here is that if I have a perpendicular bisector, any point that's on that bisector should be the same distance away from the endpoints of the line that's being bisected. Okay, that's what I'm trying to prove here. And so over here I have M as a perpendicular bisector, and then I have some point C that's on M. I just want to prove that C is the same distance from A as it is from B. Okay, the same distance to each of those endpoints. And so I'm going to add to this picture a little bit. That's the first thing I'm going to do. First of all, perpendicular bisector, understanding what that means, it means that this thing bisects this guy, which means these two pieces are congruent. It also means that these are perpendicular, so I'm going to label those as perpendicular lines. And then from here, I might add to this a little bit. If I want to prove that these distances are the same, I should probably label that distance with a line segment, so something like that. I want to prove that it's the same as that distance right there. And so I kind of create this sense of triangles being developed here. And that's good because we know a lot about triangles and proving things about triangles that are the same or different and that kind of thing. Okay? And so when I look at this thing, hopefully the first thing you notice right away is that I've got two sides matched up of each of those triangles. I almost have an angle matched up. I really have an angle matched up, but I have to kind of be careful about how I label it. I'm really close to being able to show that these two triangles are the same, which would make it really easy to show that CA and CB are the same. Okay, and so that's kind of where we're going with this proof. So let me do my statements and reasons here. And so as I look at this thing, the first thing I'm going to do, of course, is start with my given. And just says that M is a perpendicular bisector of AB. And I'm writing a little small. I know that I am going to be a little pressed for space on this one. All right, and that was given. All right. Next, I'm just going to write down what I've already kind of added to the picture, all right, because of what I know a perpendicular bisector to be. Since I know a perpendicular bisector bisects the thing, now I know that I don't have a label on this. I'm going to call it AD. Let me come over here, and I'm going to label this point D right here. So I'm going to say that AD is congruent to BD. And also, I know that I have some right angles here. And instead of having to label these as angle ADC, I'm just going to put like a little 1 and a 2 here to label those angles. Makes it really easy for me as I write my proof. So I'm going to say that angle 1 and angle 2 are right angles. And again, I know that because, well, that's what it means for something to be a perpendicular bisector. Okay, so that's the definition of a perpendicular bisector. Okay, and now from here, I have to think about what I know. If I know that those two angles are right angles, I immediately know that they're congruent to one another. So I'm going to say that angle 1 is congruent to angle 2. And that's because all right angles are congruent. Okay. And so now I'm really close here. I've got two sides matched up. I've got an angle matched up. All I need is something like another side here. And right away, I should recognize that CD is one of those overlapping pieces. So CD is congruent to itself. And that's my reflexive property. And so if I come up here, let me label that as well. What I have here is I have a side, an angle, and a side congruent to a side, an angle, and a side of the other triangle. I can say that these two triangles are congruent because of side, angle, side. Sorry, I switched colors there. So right here, I'm going to say triangle ACD is congruent to triangle BCD. And again, that's because of side, angle, side. And so now if I know that those two triangles are congruent, it means all of the different parts of those triangles are congruent. So I can say that CA is congruent to CB, and that's because of CPCTC. Okay, corresponding parts of congruent triangles are congruent. And now here's the thing, if those two things are congruent, well, that's what it means to be congruent is that the two lengths are the same. So now I can say that CA is equal to CB. Okay? And yeah, that's one of those kind of technicality type of steps, but that's the definition of things being congruent. Okay? If they're congruent, if the shapes are the same, it means their lengths are equal. Okay? And that's it. We've made it to the end of the proof here. And really, since C is just kind of any random point that's on M, that means that anytime we have a perpendicular bisector now, any point that's on that perpendicular bisector is automatically going to be congruent, going to be equidistant from those two endpoints, okay? And we can always show that through these kind of congruent segments, all right? So the perpendicular bisector theorem just says this. If a point is on the perpendicular bisector of a segment, then it's equidistant from the endpoints of the segment automatically, okay? And we can do the same thing in reverse. We have the converse of this thing, all right? If a point is equidistant from the endpoints of the segment, then it's got to be on the perpendicular bisector, okay? So we can use this kind of either way. If we have a perpendicular bisector, every point on there is equidistant to the endpoints, okay? If I have a point that's equidistant to the endpoints, it's on the perpendicular bisector, okay? I could draw a perpendicular bisector through that point then, okay? For example, if I look at something like this, and again, these come up a lot when we're talking about triangles. Triangles are a good source for where we kind of see some of these things pop up. And so if I look at this guy, what I see here is I see a perpendicular bisector running down the center of this triangle. And so if I have a perpendicular bisector here, it means that, and so again, if I kind of highlight this, so here's the perpendicular bisector, is this line right here. This is the line segment that it's bisecting, okay? And so what happens if I kind of think about these points on the end, sorry, I kind of overdrew that. But if I think about these points on the end, well, any point that's on this perpendicular bisector, say this point right here, okay, that's at the tip of this triangle, has to be equidistant to each of those endpoints, which means that this distance right here and this distance right here have to be the same, okay? And, you know, when you think about kind of the perpendicular bisector theorem, and you think about what we know about isosceles triangles, all right, these kind of go hand in hand, all right? And we've talked about isosceles triangles from this perspective of the base angles being congruent and some of the different things we have here, but really the perpendicular bisector theorem, Well, just shows us kind of isosceles triangles when this thing is all said and done, okay? So they're very similar, they're very closely related, but any point that's on this perpendicular bisector has to be the same distance to each of the endpoints, which means in this scenario, the 4x has to equal the 6x minus 10, okay? And now I can solve this. I'm going to subtract the 6x from each side. And I'm going to divide by the negative 2, so that gives me a 5. And so for this one, I found that x equals 5. I could even find the length of each of these. And the nice thing about finding the length of each of these, if you were to plug them in, here you get a 20. Here, if you plug it in, you also get a 20. So it's kind of an instant check here. So depending on what the question asks me, x is a 5. The length of each of those, the distance of that point is 20. Okay? If I look at the next one here, the angle bisector theorem. So this time, instead of doing a perpendicular bisector, now we're doing an angle bisector. And this is a very similar type of theorem, except instead of having endpoints that we're equidistant to, we're actually going to be equidistant to the two rays that formed the angle. Okay? So if BD bisects ABC, angle ABC, and DA is perpendicular to BA, DC is perpendicular to DC, I want to prove that DA is equal to DC, that those two lengths are the same. And again, all we're doing here, the whole idea of the perpendicular lines that are in here are just showing us that we're measuring the distance, okay? We can only measure the distance if we're measuring at a perpendicular angle. All right, we have to go the shortest distance from one thing to the other. So the reason these perpendicular lines are in here are to show us that we're measuring the distance from point D to that ray BA. Okay, we're measuring the distance from point D to that ray BC. Okay, if I had drawn a line that kind of went like this, I wouldn't be measuring. When I look at that segment that I've just drawn, that doesn't measure the distance between D and that ray. All right, because I'm taking a route that's not the closest route to the thing, okay? And so that's what the perpendicular lines are kind of serving the purpose of. They're serving the purpose of us showing the measurement between the one thing and the next, okay? And so really what this amounts to is I'm trying to prove that point D, that point that's on that angle bisector, is the same distance away from each of those rays, okay? I'm trying to show that this distance and this distance are the same thing. And so it's a very similar proof to what we just did. The previous proof, we were trying to show that the point was the same distance from each of the endpoints. Well, now I'm trying to show that any point on this thing is equidistant to the two rays, okay? And so let's go ahead and set this thing up. And we might label some extra things up here as we go. So statements and reasons. And when we recognize that it's really kind of trying to prove the same type of thing, it makes this a lot easier because we're going to kind of go the same route, all right? So let's start with what we know. We know that BD bisects angle ABC. And we also know that DA is perpendicular to BA. We know that DC is perpendicular to BC. And again, I need those to be perpendicular just so that I can show that I'm measuring a distance here. And that was given. And now from here, I just have to kind of maybe label some of these things. I'll call this angle 1 and angle 2. And so as I look at this thing, maybe 3 and 4 over here. Let's label those. And so as I look at this, first of all, an angle bisector basically splits this thing into two congruent angles. So the first thing I might say is that angle 3 is congruent to angle 4. And you don't have to start with that. I could have started with 1 and 2, all right? But I know that because that's what a bisector does, okay? That's the definition of an angle bisector. Okay? I can also say that angles 1 and 2 are congruent. That's because all right angles are congruent. And, we could have split that up and said, hey, 1 and 2 are right angles because of the definition of perpendicular lines, and then said they're congruent because of all right angles are congruent. All right. But again, just kind of shortening this up a little bit, there's that idea of reasonable justification. And so as we look at this thing, again, I've created two triangles here. And in those two triangles, I have two angles that are congruent. All I need is a side to be congruent in order to prove this by either angle, side, angle, or angle, angle, side. The obvious side that we have is BD being congruent to itself. So once again, kind of using that overlapping piece, BD is congruent to BD. And that's our reflexive property. And so now what I have here, if BD is congruent to itself, well, now I have angle, angle, side, all right? And so I can say that these two triangles are congruent. So we're going to say triangle, I'm going to call it BAD. Congruent to triangle BCD. And again, that's just angle, angle, side. And now I can say that the pieces are congruent, and it looks like I kind of ran out of space here a little bit. So I'm going to say that CD, or sorry, I guess I'll label it the same way that it is in the proof statement. I'm going to say that DA is congruent to DC, and that's because of CPCTC. And now my last little step here, I'm going to say that DA is equal to DC, because that's what two things being congruent really means, okay? So definition of congruent. Okay, but again, similar style of proof, and it kind of gives me a similar type of thing, all right? So when we look at this, it just says, hey, if a point is on the bisector of an angle, then that point is equidistant from the sides of the angle, okay? It's equidistant to those two rays that make the angle, all right? Very similar to the previous thing, all right? And then, of course, the converse of that is also true. If I have some point that's floating out in this angle and that point is equidistant from the two sides of the angle, well, then it must lie on the angle bisector, okay? And so it would allow me to draw the angle bisector, and that's one of those things that's really important. Like when we have to add things to proofs later, when you have to draw a line in somewhere, this theorem kind of allows me to do that. It allows me to say, hey, I can put a point here that's equidistant here, and it's on the angle bisector, all right? It kind of opens up a lot of possibilities. So looking at an example of this thing, if I had something like this guy, here I know that this thing is an angle bisector, and I know that because right here it's saying that these two angles are congruent. And if those two angles are congruent, it means I have an angle bisector, which means every single point on here is is equidistant from the two ends. Like if I were to draw this point right here, the distance here and here have to be the same. If I were to draw this point right here and measure the distance, these two would have to be the same. Okay? Any point that's on this thing is going to be equidistant to those two sides, including the point that's drawn up here. All right? So this point right here has to be equidistant, which means this guy is congruent to this guy, which means the 7x has to equal the 2x plus 25. And so now I can finish solving this thing. I subtract the 2x. I divide by the 5. So I find out that x equals 5. And of course, if I wanted to actually find out, hey, what is the distance from the sides to that point, I could plug it back in. Here I get a 35. And here when I plug it in, I also get a 35. And so once again, it kind of instantly checks itself. But again, any point that's on that angle bisector will be equidistant to the two sides. That's what we came up with as we went through this proof. Okay. So the two big things today, again, a segment bisector, when I draw the perpendicular bisector of a segment, any point on that bisector is equidistant to the two endpoints. Okay? When I draw an angle bisector, any point on that angle bisector is equidistant to the sides of the angle. Okay? And of course, the converse of each of those is true.